Hey there, and welcome. Have you ever stopped to think about the invisible material that basically holds our modern world together? It's in your car, it's in your house, it's even in the hospitals that keep us safe. Today, we're going to pull back the curtain on the hidden fabric of our lives. I mean, really think about it for a second. On the surface, they seem like they have absolutely nothing to do with each other, right? You've got medical gear, a personal hygiene product, and a piece of a car. But they all share a secret connection.
And the answer is non-woven fabric. It's a type of textile you have definitely used, probably hundreds of times, maybe even today, without ever really knowing what it's called. So let's dive into what makes this material so special and so versatile. All right, here's our game plan for today. First, we'll get into what a non-woven actually is. Then, we're going to explore the 4 main recipes for making them, using brute force, heat and glue, and even some seriously high-tech spinning. And finally, we'll see how each method gives us the perfect fabric for any job.
Okay, first things first. What in the world is a non-woven? When you think of fabric, you probably picture threads or yarn woven together or knitted in a pattern, kind of like your t-shirt. Well, non-wovens basically take that whole idea and toss it right out the window.
And here's the key difference, the big idea. Non-wovens completely skip the whole step of spinning fibers into yarn. Instead, they take a messy web of loose fibers and just bond them directly. This direct-from-fiber approach is what makes them so incredibly versatile and, frankly, so efficient to make.
You can think of these methods as different recipes in a cookbook. Each one uses a totally unique process to turn those loose fibers into a real, functional fabric. And as you'll see, each recipe results in a material with very, very different qualities.
So, we're going to walk through 4 main production families: mechanical, chemical, thermal, and the really advanced spunlaid processes. Let's kick things off with the one that's all about pure physical force.
This method is maybe the most intuitive. To get a bunch of fibers to stick together, you force them to get tangled up. It's kind of like creating a massive, perfectly controlled knot, but on an industrial scale.
The process is actually pretty cool. Imagine thousands of tiny needles, but they're not smooth needles. They have little barbs on them, moving up and down like crazy, punching through a web of fibers. Every single punch grabs some fibers and yanks them downwards, tangling them all up. You do that millions of times, and you get a really dense, almost felt-like fabric.
Now, this process creates an incredibly tough and durable fabric. It makes sense, right? That's why it's perfect for things like carpets and the liners inside your car. And get this, it's also super important for big infrastructure projects like the geotextiles used to stabilize the soil under India's national highways. They provide strength and help with drainage.
But what if you need strength, but also softness? Well, instead of needles, you can use water. With hydro-entangling, you've got these superfine high-pressure jets of water blasting the fiber web. And it's the sheer force of the water that twists and tangles the fibers together.
And because you're using water instead of thousands of sharp needles, the fabric you get at the end is so much softer, more flexible, and really absorbent. This makes it absolutely perfect for things that touch our skin, like disposable wipes, medical gauze, that sort of thing.
So, let's put them side by side. You've got brute force versus a more focused force. Needle punching gives you a stiff, durable mat that's great for a carpet. Hydro-entangling gives you a soft, absorbent sheet that's perfect for a wipe. 2 mechanical methods, 2 completely different outcomes.
Okay, so we've seen how physical force can mash fibers together. But what if we use something else entirely? Our next 2 methods are all about bonding fibers using either heat or a type of glue.
So this method only works with what are called thermoplastic fibers. Think of them as plastics that get soft and melty when you heat them up. You pass a web of these fibers through massive heated rollers. It's like a giant industrial ironing press. And wherever the fibers touch, they melt just a little and fuse together as they cool, creating a bond.
What you get from this process are these incredibly lightweight, soft, and really uniform fabrics. This is the technology behind the soft layers you find in diapers and sanitary napkins, products where having a smooth, comfortable feel is absolutely everything. All right, our next method is probably the most literal one we've talked about: chemical bonding. Here, you're basically applying a chemical binder. Think of it like a liquid adhesive to the web of fibers. You can spray it on, print it in a pattern, whatever you need. As that binder dries and cures, it glues all the fibers together.
Now, depending on the kind of glue you use, these fabrics can be made pretty stable and even stiff. You'll find them as the inner linings that give shirt collars their structure, or in certain disposable filters where you need stability more than you need softness.
Okay, now for our final category, the spunlaid method. And honestly, this one is a total game changer. Instead of starting with fibers that are already made, this process starts with raw plastic pellets, polymers, and creates both the fibers and the fabric in one single continuous high-tech step. Now, there are two main types to know here. Spunbond pushes out long, continuous filaments of plastic to make a really strong, durable web. Meltblown, on the other hand, uses hot air to blast that same plastic into incredibly fine microfibers, creating a web with amazing filtration power. But here's the magic. They're often combined, sandwiching a delicate meltblown layer between two strong spunbond layers to create a composite fabric called SMS. This SMS composite gives you the best of both worlds. The strength from the spunbond layers protects the delicate filter layer from the meltblown. This is the exact technology used in high-efficiency face masks and surgical gowns. In fact, during the pandemic, ramping up domestic production of these materials became a huge focus for initiatives like Make in India, which just shows how critical this tech is for our health. Wow, okay, we have covered a lot of ground, from punching fibers with needles to literally spinning them out of melted plastic. So let's bring it all together and see how these different recipes create the perfect fabric for a specific job. So here it is, all in one place. If you need serious strength and durability for something like geotextiles, you're going to choose mechanical bonding. If you need stability and stiffness for a shirt collar, you use chemical bonding. For that critical softness and lightness in a diaper, thermal bonding is your answer. And for the high-tech filtration and strength needed in a face mask, the spunlaid process is the only way to go. You see? Each method gives the final fabric a unique superpower.
So, the next time you use a wipe or put on a mask or even just sit in your car, you'll know the secret of the hidden, non-woven fabric that makes it all possible. And it leaves us with a final thought, right? As this technology continues to advance, what new problems will these invisible fabrics solve for us next?